He works in derived algebraic geometry, and indeed his series of papers with Gabriele Vezzossi, along with those of Jacob Lurie, form the foundations of much of this subject, which is a far-reaching generalization and unification of algebraic geometry and homotopy theory and other things. His best-known paper here in Oxford is his paper with Vezzossi, as well as Tony Ponteff, who is here, and Vaquier, on shifted symplectic structures, which allowed the group here to make progress in other things. But he's known for many other things around this subject. He was a speaker at the ICM and has other distinctions to his name. But I think you will want to hear him, so why don't I invite him to give a talk on algebraic geometry, categories, and the trace formula.
Thank you very much. Thank you very much for the invitation and for allowing me to give this talk. It's always a great pleasure to be in Oxford. And what I will talk about today, I want to present a conjecture called the Bloch's conductor formula. And I want to show you a possible approach to a proof of this conjecture. But I will start to spend a good part of the talk to explain what it is about. And at the end of the talk, I will explain what are the new ideas to try to prove this conjecture. So let's start with a very fundamental question in algebraic geometry, which is the question of topology of algebraic varieties. It's a very simple question. You give yourself a finite number of homogeneous polynomials, F1, Fp, say with complex coefficients, and you look at the subset in the projective space where these polynomials vanish. And the general problem is you want to say something about the topology of this X inside the projective space, and you would like a way to read the topology out of the equations. So it's a very general question. It's very wide in the sense that it has many possible answers. It has many possible approaches. And in this talk, we will focus to one specific aspect. You will see in a moment. So that's the general question I want to talk about now. So what are the typical answers in low dimensions? There are two very famous statements. Assume that we are looking at an homogeneous equation with two variables of degree d, and if I look at x, it's a finite set, and this finite set comes with a discrete topology. So if I want to understand the topology, I just have to count the number of points in this finite set, and you all know that this number of points is the degree of the polynomial. Well, there are some, you will see that there are some colors in this talk. So there is the gray thing here, which is some extra information. So of course, I have to count with multiplicities, but I will assume that we are in a generic situation. Okay. And the other very famous case is for a plane algebraic curve given by one equation. And so X is a compact Riemann surface, and its topology is characterized by an integer called the genius. And this genius is given by this number here in terms of the degree of the equation. Again, I mean, if X comes with singular points, then this G of X is the arithmetic genius and not the geometric genius. So that's the kind of answers we are looking at. Understanding topological informations of the set of solutions of these polynomial equations in terms of the equations themselves or in terms of some invariants constructed out of the equation. So let me focus on one very simple topological invariant called the Euler characteristic. So I look at it, I consider X, and I just look at the alternating sum of its Betti numbers. And I want to evaluate this integer. And if I go back here, you see that what we compute here the Euler characteristic of a compact Riemann surface is completely determined by its genus, and the Euler characteristic of a finite set of points is just a number of points. So this is actually what we are computing here. There is a theorem, which is something also very well known, that this Euler characteristic can be computed by another Euler characteristic involving the cohomology of X with coefficient in differential forms. So here, this omega q is the sheaf of holomorphic differential forms on X. And I want to emphasize here that this right-hand side, even though it involves holomorphic differential forms, is something you can compute purely algebraically by means of the famous Gaga theorem, telling you that you can turn here holomorphic or algebraic, it gives the same answer. So we have a nice formula for the Euler characteristic of a complex algebraic variety in terms of something that can be computed algebraically. I mean, it's not something easily describable in terms of the equations, but still, you can start from the equation, construct, say, a ring, and out of this ring, you can construct by a purely algebraic way this number here. So, when I prepare slides, my friend and co-author Gabriele Vezzosi always complains. He always complains that there are not enough colors in the slides. So I will try to put colors as much as possible in this talk. They will have a meaning. So the blue color is about topological invariance, and the red color is about algebraic invariance. And in this formula, what is important is that we have a connection between topology, the blue side, and algebra, the right-hand side. We will have two more extra colors, green and brown. Yeah, I don't want to spoil now, telling you what they are, but you will see in a moment. And that's really the, maybe the most central question in algebraic geometry, to relate topological invariance and algebraic invariance. Okay, if you want to understand why this formula is true, over the complex numbers there is an easy reason, which is the Hodge decomposition. So the cohomology of the space, the cohomology of the space here actually has a decomposition in terms of the cohomology of the differential forms. So if I compute the dimension of Hi, I get the sum of the dimension of HP x omega q, and it gives automatically this formula here. So Hodge theory gives you the formula about Euler characteristic. But there is something more general. There is an independent proof which has nothing to do with Hodge theory. Well, you can use a Gauss-Bonnet formula. So GB is for Gauss-Bonnet, saying that the Euler characteristic can be computed by integrating a differential form which is a top Chern class of the variety X. And you can add another formula called the Hirzebruch-Riemann-Roch formula, telling you that the integral of the top Chern class can be written as is also this number. So if you put Gauss-Bonnet and Hirzebruch-Riemann-Roch, you get another proof of this formula here. So there is a proof by Hodge theory, but there is also an independent proof using Gauss-Bonnet and Hirzebruch-Riemann-Roch. So now these two formulas, Gauss-Bonnet and Hirzebruch-Riemann-Roch, are true for any algebraic varieties over any fields. I don't need my polynomial equations to be defined over the complex numbers. I can have polynomial equations defined over a field, K. So now I'm changing a little bit the context. My polynomials are defined over little k, and little k is going to be an algebraically closed field. It can be C, but it can be something of positive characteristic. It can be the algebraic closure of a finite field, for example, or it can be a number field, or the field of algebraic numbers, and so on. And I asked the same question. Now there is something, the formula remains true, but I have to define the left-hand side, which is the Euler characteristic, not using the usual cohomology of X, because Now my base field is not the complex numbers anymore, so I don't have access to the usual topology on the complex numbers. And I replace the left-hand side by the Euler characteristic. There is a -1 to the I missing here. Sorry about that. This is the alternating sum of the dimensions, where these groups now are the L-adic cohomology groups of X. I'm not going to explain how they are constructed. They have been introduced by Grothendieck in the late 50s and the 60s. And they behave like cohomology of a topological space or a topological manifold. They satisfy all kind of properties, such as Poincaré duality and so on. And the same formula is true with the -1 to the I, of course. And the reason is really this thing. So first, if you think about Hodge theory, there is a feeling that this formula has something to do with the Hodge decomposition, but it's true in general, and it has nothing to do with the Hodge decomposition. And there is a warning that in general, if I fix I, the dimension here is not the sum of the dimension here. So it's only after taking the alternating sum, and there are some constellations involved in this formula. So individually, this HPQ, these cohomology groups can be wrong in the sense that the sum of these things might be bigger than the dimension of this group here, but if I take the alternating dimension, then things cancel out and the formula is true. Okay, so this is the story for algebraic varieties. There is a formula computing the Euler characteristic of any algebraic variety over any algebraically closed field. And this formula involves these cohomology groups of differential forms. And this is a purely algebraic construction involving Schiff cohomology for the Zariski topology. So it's something you can, there is not an easy formula in terms of the equations, but starting from the equation, there is a purely algebraic process that gives you these groups here. And let me tell that this is a special case. You see the -1 to the I is here. So this formula here is a special case of something more general called the trace formula. Now I have an algebraic variety, but it comes with an endomorphism. So it comes with a map from X to itself, defined by polynomial equations. And then this F acts on the cohomology. And I can evaluate the trace or the alternating sum of the trace of F on the cohomology groups. That's on the topological side. And the trace formula tells you that this is given by another number, gamma F dot delta X, which is an intersection number of the graph of the endomorphism with the diagonal inside the product. So this intersection number is really on the algebra side. It's something you can compute purely algebraically. And the left-hand side is on the topology side. And of course, when F is the identity, if you take the identity of X to itself, this recovers the formula we just had. Because the trace of the identity becomes the alternating sum of the dimensions, and this intersection number becomes the self-intersection of the diagonal, and the self-intersection of the diagonal can be computed using this Hodge cohomology. Okay. Now I want to study something a little bit more complicated, and it's related with the fact that in nature algebraic varieties arise in families. So and most of these so they usually arise with parameters. So there is you have families of algebraic varieties parameterized by another algebraic variety, and sometimes when you specialize the value of the parameter, your variety becomes singular. So it's something which is extremely ubiquitous in algebraic geometry. It's not something it's not accident, so it's accidental or anything. It's something that happens a little bit everywhere. So I give you here two examples where you have this degeneration from a smooth variety to a singular one. The most famous one is the compactification of the moduli space of Riemann surface of genus G with n marked points. where to compactify, you add at infinity some singular curves with ordinary singularities, for instance. So that's the first example. So in moduli theory, when you want to construct moduli of algebraic varieties and you want these moduli to be compact, you have to add at infinity most of the time singular varieties. And there are other situations coming more in arithmetic geometry where you can have varieties defined over a number of fields, and so you can, your polynomial equations the coefficients of the equations are in a number field, so they are defined essentially everywhere on the ring of integers, and you can say take your equation and mod out by a prime ideal. So typically you have equations with z coefficients, and you mod out by p, you get an equation with coefficient in the finite field. But it happens often that you have primes which are with bad reduction, meaning that the variety you get after modding out by a prime number is a singular variety. And these two phenomena are, you encounter them very often. So it's very natural to look at the question where you don't have just a variety, but you have a variety that varies in a family, and it degenerates to a singular variety. So what's the setting for this? Now, it's the same setting as before. I have homogeneous polynomial equations, but the coefficients of these equations are in a ring A. And this ring A is the ring of functions on a space of parameters S. I will give examples of what S is in this talk in the next slide. And now I look at the subspace inside the projective space times S, where these polynomial equations vanish. And this X is something that sits over S and is the total space of a family of algebraic varieties. So if I pick a point in S, then I get a fiber. So it means I fix S, I get something inside the projective space, and it is defined over a field which is the residue field of the point in S. And you will see examples in the next slide. This residue field can change. So there is this thing that, this is what I was explaining, from start with some equation over Z and you get an equation over a finite field, or you get an equation over Q by just embedding Z into Q. So the field of definitions of your various varieties parameterized by S changes with the point. Okay, these are the examples I want to consider. I want S to be something like a small disk. So the technical terminology, it's an Enselian tray. And the typical examples are this one. I can take, so this is my ring A, right? This is A, the ring of function on S. So A can be formal power series over the complex numbers, or the formal power series over a field K, but it can be also something like the p-adic integers, or it can be something like a finite extension of the p-adic integers. And you see, in this case, you actually get a family of complex algebraic varieties. So it's the intuition behind this first case is really you have a family of polynomial equations, and the coefficients are like holomorphic functions or maybe just formal functions. But in this case here, you typically have equations where the coefficients are in p-adic numbers, and you can either embed ZP inside QP and get an algebraic variety over p-adic, the p-adic fields, or you can actually mod out by P and get an algebraic variety over a finite field. Okay, so in all these cases, my S is the spectrum of a complete DVR. And what I want to emphasize is that it's a space with only 2 points. There is a special point, which is it corresponds to the ideal generated by the T here. Here's the ideal generated by T, and here's the ideal generated by P. And there is a generic point, which is just embed this ring inside its fraction field. So this residue field I was mentioning on the last slide, it's either the quotient of A mod its maximal ideal here, or the fraction field of A. And from my family X over S, I get two varieties. One is defined over the residue field, which is obtained by modding out the coefficients by the maximal ideal. And the other one is the generic fiber, which is you embed A inside its fraction field, and you get a variety over the fraction field K. And I put little bar, meaning that I want to extend these to algebraic closure and consider them as algebraic varieties over algebraically closed fields. So this is the setting of a family of algebraic varieties parameterized by S. Now, the variational version of the problem I was mentioning before is you want to understand now how the topology changes when you go from the generic fiber to the special fiber. So on the first slides, I was explaining how to compute the Euler characteristic of such a thing. Now I want a formula that gives you the change of the Euler characteristic. So this variational problem is to evaluate the difference of the two Euler characteristics in terms of algebra again. In terms of, so that's going to be a blue thing, and I want a red thing. So the first observation is that if your total space X, which maps to S, is a submersion, so intuitively you want to say that on the level of tangent spaces it is surjective, then these two varieties are smooth, so they don't have any singular points, and the topology is constant. So it's known that the Euler characteristic is preserved. So there is nothing happening when this map is a submersion. So this problem is only interesting when there is say we go from a smooth variety to a singular variety, and this is what we're going to assume. We're going to assume that the generic fiber, so the variety you have on the fraction field of A is smooth, but maybe this variety obtained by reducing mod the maximal ideal has singularities. So there is a solution to this problem over the complex numbers, which is, it comes back to Milnor. It goes back to Milnor, and the version I'm writing here, I think, is due to Kapranov, and there is an independent proof by Saito. And there are more recent results telling you that this is true in a stronger sense, not only at the level of Euler characteristic, but maybe individually on the cohomology groups. So the formula says that this difference of Euler characteristic between these two varieties is given by, again, something that looks like the cohomology of X with differential forms. But now there is an extra differential here on the forms, which is wedge df. And f is the function on the total space, which corresponds to putting back the coordinate on the small disk S. So S is a small disk. It has a coordinate, which is little t or little p. Put it back to X, it gives you a function. I can take the differential of this function and wedge with it. And I get a complex of forms, and this is the cohomology of X with coefficient in this complex. So this is what it is concretely. You have the sheaf of functions going to the sheaf of one forms, which is just the differential of f, and then it's just wedge, and it gives you a complex like this. And you take the cohomology of that on X. So this formula, if you write it in the case where the special fiber has only isolated singularities, is what is known as Milnor formula. So Milnor formula is something telling you that the space of vanishing cycles has the same dimension as the Jacobian ring. And one interpretation of this is exactly this. So the Jacobian ring, for isolated singularities, this is exact, and the only cohomology is in degree n. And in degree n, you find exactly the Jacobian ring. So for isolated singularities, this is just Milnor formula. And Kapranov gave a proof that this extends to any kind of singularities. And I think Saito, and then later Efimov, Kontsevich, Preigel, Saba, I don't know, many people gave a proof that this is much stronger and you can actually prove something on the level of cohomology groups rather than just Euler characteristic. So that's the solution for in characteristic 0. Now in any characteristic, there is a conjecture, and the situation is more complicated. So here is the brown thing. So there is something new if you don't put yourself in characteristic 0, is that you have arithmetic phenomenon or arithmetic aspects. And Deligne, first for isolated singularities and later Bloch in general, gave a formula for this difference of Euler characteristic under some assumption here. And it's telling you that it's equals to something red, so typically something of this form, which is an intersection number, and you should recognize here that it looks like the intersection number of the diagonal. I will make a comment a little bit later about that, plus something else, which has something to do with arithmetic, and it has something to do with wild ramifications. So here, the red part is the degree of a zero cycle constructed on the special fiber. And these zero cycles measures the singularities of the map from X to S. So it's called the Bloch's localized intersection number, and it's a generalization in higher dimension of something called the different. You know, when you have, in algebraic number theory, you have the different. When you have a ring of integers, there is a cycle which measures the ramifications of your extension from Z to the ring of integers, which is called the different. This zero cycle here is a higher dimensional generalization of this different. I'm not going to give you a construction of this. It's complicated. I'm going to give you another interpretation later. And this brown term is the Swan conductor, which measures the what is called the wild ramifications. It has something to do with the action of the Galois group of the fraction field on the cohomology of the special fiber. And it has something to do with the fact that this group can act by wild monodromy, which is a part of the action that factors through a finite group whose order is divisible by the characteristic of the residue field. So it's something which is typically of arithmetic nature. So that's it's a beautiful conjecture because it relates really to three different aspects of algebraic geometry in non-zero characteristics, which are the topological aspects, algebraic aspects, or say algebraic cycles or algebraic K-theory, and something purely of arithmetic nature. And depending of where you come from, you are interested in, for instance, people coming from arithmetic geometry are interested in this formula because it's a way to compute the Swan conductor by two other terms. And if you come from geometry, maybe you want to say, oh, it's a nice formula because it allows to compute the difference between the Euler characteristic. So depending where you come from, two of the terms are easy, and the third one is mysterious. And you want to think of this formula differently depending on what you want to compute. Okay, so there are some cases where this formula is true. Oh, it's stuck again. Good. So as I said before, the characteristic zero case is known, and this is this theorem I was mentioning of Milnor, Kapranov, and Saito. So in characteristic zero, this term vanishes. And there you have only two terms, and this intersection number can be written as this alternating sum of the Hodge cohomology. So this is known in characteristic zero. In a quick characteristic P, so mainly when A is formal power series over a field, there is a very recent work of Saito that proves the formula, and it's based on Bailinson's theory of singular supports for elliptic sheaves. There is a fundamental work of Kato and Saito in 2001 where they proved the formula under the condition that if you look at the spatial fiber inside the total space, you want this to be a simple normal crossing divisor, or supported by. There is also a trivial case, which is when, this eta bar is big K bar, that's the generic fiber. The degenerate case is when your family is constant over the spatial point, so it's the generic fiber is empty. I mean, most of algebraic geometers won't consider this as a family of algebraic varieties. I do consider this as a family of algebraic varieties. You can have the empty variety degenerating to a non-empty variety. It's a very degenerate family, but still it makes sense. And if you write down the formula, you recover the formula for the Euler characteristic of X in terms of these Hodge numbers. So that's an important comment here, that this degenerate case is what I was mentioning on the very first slides. The formula for the Euler characteristic of a single variety is a special case of this variational thing. And then you have the case of a family of curves. So Bloch himself proved this case. And a finite ramified cover, so the relative, it's a family of points, if you want, family of varieties of dimension 0. And that's extremely standard. This is in, you can find this in books in algebraic number theory. It's just the standard formula for the difference. So this difference is a cycle. You want to compute the degree or the length of some sheaf supported at 0, something like this. And the length is given in terms of higher ramification groups. And this is exactly what is the formula about. So it's known in these two cases. In general, it's open. So in mixed characteristic, typically when you are over p-adic numbers or finite extensions of p-adic numbers, and particularly outside of this case, of course. So for instance, for isolated singularities. So this condition here tells you that the singularities of the spatial fiber are in a low codimension. So it cannot be isolated singularities except if it is a family of curves. So that typically the original conjecture of Deligne, which is, I've seen the name Deligne-Milnor formula, is an open question. Okay, so we have this conjecture, and of course we would like to prove it. And here is the fourth color. So we want to make progress on this, and we want to bring a new point of view or a new a tool to the game, which is non-commutative geometry. So it goes back to the comment I made a minute ago about this degenerate case where you have this funny family where the empty variety degenerates to the non-empty variety. You want to think that this degenerate case is the commutative case as opposed to non-commutative. And that the general case is like a non-commutative perturbation or a quantum perturbation of this very special degenerate case. And if I talk about non-commutative deformation, there should be a parameter perturbing the situation, and the parameter is really a choice of uniformizer in A, which means choosing a coordinate on S. So this coordinate on S that defines a function on F, this function is really the parameter I'm talking about that will that we will use to do a non-commutative deformation of this degenerate case somehow. So that's the idea which is behind this non-commutative geometry approach. Okay, so I have. So what we're going to do now, we're going to introduce a non-commutative space, xp. So p here is this function. And we want to say that, there are many things. We want to say that the Euler characteristic of xp is the difference of the Euler characteristic. There is a chi missing here. And if we can find such a thing, we want just to apply the non-commutative trace formula for this space for the identity. So we want to compute the Euler characteristic of this thing by means of a trace formula for this non-commutative space. So we have two things to do. We have to find a non-commutative variety. Well, there is three things to do. I have to tell you what non-commutative varieties are. Then we have to find one satisfying this. And of course, I have to give a sense to what's the Euler characteristic of such a non-commutative guy. And then I have to tell you something about the trace formula. Okay, so let me spend some time discussing non-commutative schemes or non-commutative varieties. So here's the definition. A non-commutative variety over some base, K, so K can be a ring. It's going to be a field at some point, but it can be a ring. It's just a K-linear category. I think I have some time to remind what it means. So it's a very simple data. It consists of just a set of objects. And between two objects, I will have a K module of maps. And I put DG here. And this DG corresponds to complex of. In the sense that it's not only a K module of maps, there is also an internal differential. So there is a differential on this K module here. So it's a graded K module with a differential. And I have composition maps, which are maps of K modules compatible with the differentials. And it must satisfy associativity and unity. So it's a very simple algebraic data. And it sounds like a silly definition. I don't know what it does to you, but it sounds like a silly definition. Because K-linear categories or K-linear DG categories are already defined, and I'm just renaming them. I'm just saying something that has a name has another name. And it's hard to believe that this is going to be interesting at all, but it's a fact that it is. And maybe also one comment about this definition. This is absolutely not a personal definition. This is a folklore definition that is used since 20 years now, I think. So I think it goes back to the work of Bornal, Orlov, Vandenberg, Kapranov, Kontsevich, many others. So it's a very folkloric definition. Any category is a non-commutative variety, and vice versa. There is a small thing I'm not telling you about, is what are maps between these things. So we have to consider these objects up to a notion of equivalence, which is a complicated thing called Morita equivalences. And it's not really possible to explain this in this talk, but you have to think that these data here are like a set of generators for something more complicated, which is a triangulated category associated to this. And you want to say that two different things can generate the same triangulated category, and you want to identify these two things. So just keep in mind that the definition is easy, but the maps between these things involve some non-trivial definitions and results and so on. So there is the technical part is hidden in here. But to define a non-commutative variety or a non-commutative scheme, it's very easy. I just have to define a category. So it's a very weak definition, as I said. So the good part is that you have plenty of examples. I mean, really plenty of examples. In a way, too many examples. So if there is examples coming from algebra. If you just pick any K algebra, you have various constructions to look at it as a category. One way is to take the category of complexes of A modules. That's an example of a DG category over K. You could also consider the algebra as a category with one object. It's another way to look at it as a category. So any algebra gives you a non-commutative variety. Any scheme gives you a non-commutative variety because schemes are locally given by a K algebra. So you can glue these things to get D of X. So when X is an affine variety, this is just D of A for the ring of functions. But in general, it's a gluing of these things. And you have many other examples that comes from Quiver, topology, or symplectic manifolds. You can take the Fukaya category of a symplectic manifold as an example. You can take the category of representation of a quiver. These are the categories of, local systems on a space. There are really plenty of examples. That's the good aspects of having a very weak definition is that you have a lot of examples. Now, the bad aspect is that a very weak definition, it's hard to believe that it gives you something interesting, right? And in fact, if you start playing with this, you know, when you define schemes, or when you want to work with a notion of varieties, you want to be able to do geometry with this. So now, if you try to do geometry with these non-commutative varieties, you won't be able to. So there is no geometry, really. No geometry means you cannot say what an open subset means, or if you do so, it's the only possible definition is going to be meaningless. You cannot say what points are. So these are really, in terms of standard geometric intuition, these are very pathological objects. So this could be the end. I mean, plenty of examples, but essentially no geometry. And there is a good surprise. And again, this is not something new. I think it goes back at least to the work of Alan Kohn, which was outside the algebraic context, but it's the fact that these non-commutative schemes or non-commutative varieties, even if they don't have geometry, they have cohomologies. And that's something. I mean, for me, it's really surprising. So we can define differential forms. It's known as a Hochschild homology. I will give you the precise formula in the next slide. We can also define a Laddick homology. That's a more recent thing, and it's hard to believe because there are no geometries. There is no notion of spaces. So in general, when there is a cohomology, it means that there is a space somewhere, or at least something that looks like a space, of which you can take the cohomology. This is not the case. So you have to extract some cohomology directly. But that's the good surprise of the theory, and this is what makes it very useful because we have a lot of examples. We don't know how to do geometry, but we know that we can take the cohomology of these examples and try to play with them. Okay, so let's start with differential forms. So there is a purely algebraic construction. I will assume that my category is just an algebra for simplicity, and there is this Hochschild complex. Just take the various tensor powers of B, and the differential is given by this formula involving, you just use the product in B to produce this formula. It's a complex, and the cohomology of that complex is called Hochschild homology, and it turns out that it's a very good notion of differential forms. So well, the first thing to say is that it extends. I gave you the formula for an algebra, but it extends to any DG category. So for any non-commutative scheme, we have a Hochschild complex. And it is a reasonable notion because of the following theorem called Hochschild-Costin-Rosenberg. That if I start with a smooth algebraic variety, and I consider this variety as a non-commutative variety d of x, I compute Hochschild cohomology, I find these Hodge cohomology groups. So I find differential forms. So that's one possible purely algebraic construction of these groups. Yeah. And you see, it doesn't involve any kind of topology or any kind of gluing. It's just a purely algebraic construction. And it gives you this automatically. So the space X doesn't appear in here.
So is there a hope of recovering Hodge structure?
No, I don't think so. It depends what you mean by Hodge structures. There is a hope to recover some part of the Hodge structure, but it's purely conjectural at the moment. So in particular, what we have is that the Euler characteristic of this construction, if I take the alternating sum of the dimension of these groups, I do get the number -1 to the p plus q. So, okay, I have colors, but I don't have signs. I'm sorry about that. So -1 p plus q, of course. But of course, what is important are the colors, I mean, according to Gabriel-Levetzosi. If I take the alternating sum of the dimension, I do find this number we are interested in to compute Euler characteristic. There is also a version with an endomorphism. I was mentioning this trace formula. So if I have an endomorphism of my non-commutative variety, there is also a Hochschild complex twisted by F, and then the Hochschild constant Rosenberg becomes that for X with an endomorphism F, what you compute is some intersection number of the graph of F with the diagonal. So when F is the identity, this is the self-intersection of the diagonal. Okay. So in particular, what is important is that the Euler characteristic is this intersection number of the graph of the endomorphism with the diagonal. So it computes fixed points. Why does it? Okay. So about L-adic cohomology, so I mentioned differential forms. That's the red thing. We need a blue thing, which is L-adic cohomology, or a cohomology that looks like the cohomology of L-adic or Betti cohomology. And there is this theorem that tells you that there is a way to reconstruct L-adic cohomology, but it comes, if you compute the L-adic cohomology of d of x, you don't find back this only the cohomology of x, but the sum over all Tate twists. So there is this gray thing. Gray means it's not very important. Just remove it. So it means that you find odd and even part of the cohomology. You cannot recover individually the cohomology groups, but still it's enough to compute the Euler characteristic because of this. I can define the dimension of H0 minus the dimension of H1, and this is a perfectly fine notion of Euler characteristic. If I apply it to d of x, I would find back the Euler characteristic of x. Now there is a comment here about how this thing is constructed. I should have put this in gray because I think it's not relevant for the talk. It's an approximation by commutative schemes. But let's forget about this for the moment. I mean, it's not very important for the sequel. So there is a construction of L-adic cohomology. This is something recent. Yeah, so now we're going to talk about the trace and the trace formula. So I have to introduce this notion of being saturated. For a variety, we can say the good varieties are the smooth projective varieties. So projective is because it's compact, and smooth is without singularities because we want Poincare duality. So the good varieties are the smooth, at least smooth proper varieties because they satisfy Poincare duality. In the non-commutative setting, there is something that replaces smooth proper, which is called saturated. And it's defined by saying that it has a dual. So in a way, a category is smooth and proper if it satisfies Poincare duality. It's more or less by definition. And here's the gray explanation of what having a dual means. It means you have evaluation and co-evaluation maps. The important thing is that if you have X, a variety, and you look at it as a non-commutative variety, it is saturated if and only if it is smooth and proper. So it's really an extension of the usual notion. And then it is itself dual, and that's a form of Poincare duality. Now the thing is that you cannot express this in terms of X. It's really, this evaluation and co-evaluation maps are really maps inside the non-commutative world. They are not maps of commutative varieties. So it's something interesting about non-commutative varieties that they have these duals here. So Poincare duality is realized directly on the space itself, not just on cohomology. Okay, so for these saturated categories, plus some admissibility condition, a technical condition I'm not going to discuss, then we have the trace formula. If I give any endomorphism of T, the trace of F on the cohomology, by this I mean the alternating sum of the trace on HI, equals the Euler characteristic of the Hochschild homology, so the red thing. So we have again this blue equals red property. So a topological number is expressed as an algebraic number. And of course, if you apply this to a non-commutative variety that comes from a variety, it gives you back the trace formula of Grothendieck I mentioned at the very beginning. And it also extends to some T which are not defined over K, but which are defined themselves on a non-commutative basis. If I mention this, that it's going to be useful, that sometimes this non-commutative space can, you see my X for the block formula was living over S, a parameter space. There is also something similar for non-commutative varieties. They can live over a parameter space, which is itself a non-commutative space. And this happens in practice. Okay, let me back to the blocks conductor formula and explain how we can apply this. I fix a uniformizer, so I fix if A is ZP, my pi here can be just the prime number P. It defines a function on X because it's a function on S and I can pull it back. I can just restrict to X. So I get a function on X. And I'm introducing this notion of matrix factorizations, which is the data of a matrix factorization for P is a factorization of P as the product of two matrices. But these matrices are twisted on X by vector bundles. So I have the data of two vector bundles, two morphisms, and I need that if I compose delta with itself, I have multiplication by P. It's a bizarre definition, but it's a useful definition. And they form a DG category, so they form a non-commutative space. And the non-commutative space of singularities of X over S, by definition, is this thing. So objects are this, and between these objects, you have complexes of maps. They form a DG category in a natural way. And that's a non-commutative space I want to use. I want to apply the trace formula to it. So two examples about what these are, just to emphasize that it's an interesting notion for what we are doing. If you take just a vector space with a quadratic form as a function, so you have an affine space, a quadratic form gives you a function to the affine line, and then the pullback of the coordinate on the affine line is my function Q. Then this non-commutative space is just modules over the Clifford algebra of the quadratic form. And of course, the Clifford algebra of the quadratic form sees something interesting about the arithmetic of the base field. So it's pretty clear that this thing has some arithmetic aspects inside because of this formula. For instance, you can recover the class in the Brouwer group out of the Clifford algebra. If I look at it over the complex numbers and I assume that my special fiber has only isolated singularities, then there is this theorem by Dickerhoff that Hochschild homology in degree 0, that's the Jacobian ring. Take the germs of functions at the singular points and divided by the partial derivatives of your function. It's a finite dimensional algebra, and the dimension is actually, it's true as a space, but I want to emphasize the formula on the dimensions are the same. So we see that this non-commutative space sees algebraic aspects. So this is just to convince you that this XP is something interesting for the blocks conductor formula. And in general, it only sees the non-smooth locus of X over S. So if X is smooth over S, then it is 0. And which is compatible with the fact that there is no change in the Euler characteristic. The topology remains constant in this case. Okay, so what do we know about this non-commutative space? First, we know it's saturated. Why the gray thing tells you that it's saturated over a funny base. So it's not over little k. It's saturated over something which is itself not a commutative. It's itself a non-commutative base, but still it's saturated. If you compute the Hochschild homology and the Euler characteristic, you find this block number. So I told you that I'm not going to define this, but you can take this as a definition. And then if the monodromy acts unipotently on this thing, so you have your family of varieties, and you can turn around the singular fibers. It gives you an automorphism of the special fiber and gives you an action of the Galois group of the fraction field of K on this guy. If this action is unipotent, then the Euler characteristic in terms of this L-adic cohomology is exactly this difference. So the corollary is that the conjecture is true when the monodromy acts unipotently. Because unipotent monodromy implies that the Swan conductor is 0. So that's, it's a new case of the conjecture that comes out of this theorem. Okay, to finish, what about the Swan conductor? I mean, I told you that there is some arithmetic informations encoded in this non-commutative space. So you can recover this by tensoring your non-commutative space by the non-commutative space associated to finite ramified covers of the base. And you can actually interpret this Swan conductor in terms of these things. So how this implies precisely the Bloch's conductor formula, it's still under investigation. So it's not completely clear that we get the Bloch's conductor formula out of this, but it's a good, we are very optimistic about the fact that we can just play with this base extension here to recover the formula in general. And the final comment is that I hope I convinced you that this non-commutative space sees interesting aspects, topological, algebraic, and arithmetic. And particularly 3, actually you can completely recover the Galois action on the cohomology of the generic fiber, or the cohomology with coefficient in vanishing cycles. And because of this, we think it's interesting outside of the Bloch's conductor formula. So it's interesting also for other kind of questions coming in arithmetic geometry. And I think I'm finished.
Thank you very much. I thought I'd share something with you. I was inspired to write a poem during this talk, a very short one. Algebra is red, topology is blue, categories are sweet, and so are you, Bertrand. So thank you very much. So, any questions?
Oh, so you have this conjecture about the Bloch conductor. I'm not an expert, so I'm asking maybe a stupid question, but you have this conjecture which is about families of varieties. Is there sort of a smallest variety or smallest family of variety for which you don't know the answer to that conjecture? I mean, is there an example?
So you have to go at least to families of surfaces. So the total space should be of dimension 3. And I think for surfaces with isolated singularities, it's already not known. From what I understand, the work of Kato and Saito implies the conjecture if you know a strong form of resolution of singularities for excellent schemes. So if one day we have resolution of singularities for all excellent schemes, then the formula is proven in general. And I think the very first case is a degeneration of surfaces with isolated singularities. I won't be able to write the precise examples, but yeah. That's the very first case which is not covered by the work of Kato.
So one case of a family scheme is you take a smooth scheme and you then correct the polygon. And then talk about brittle load back. Is this an extension of this story of the minus function of symplectic things?
To which, I didn't get the question.
Is this an extension of this story into minus one shift of symplectic things, which are going to locally brittle load back?
You mean, for instance, a conductor formula? I mean, I'm not sure what you are thinking of. There is a talk tomorrow about this. Yeah, I'll try to talk about this tomorrow. So it's going to be a bit technical. But what I should say is that in the mixed characteristic case, I don't think it's true. So you see, if you have a function, you take the critical loci. Suppose you have only one singular fiber. then the singular part of the special fiber comes equipped with a derived structure, coming from the fact that it is the truncation of the derived critical locus. In the mixed characteristic case, I don't think this is true anymore. There is no, or at least I don't see how to construct a natural derived structure on the singular point of the special fiber. So it exists locally, but there are some gluing problems. But the thing is that this matrix factorization does make sense. So in mixed characteristic, it's a situation where the -1 shifted symplectic structure might not make sense really, but the quantization exists, which is this non-competitive variety. Something a bit bizarre. Which maybe mean that there are quantizations of something which are not -1 symplectic structures, something marginal.
Perhaps just one more. Great.
Your trace formula for this structure, you made this assumption admissible. Doesn't this just mean you reduce your trace formula to the geometric one?
No.
It's really
It's really a new thing, yeah. Admissibility is no, maybe I don't need the so admissibility means that so we have this cyclic homology theory. We don't know it satisfies Conet. If it satisfies Conet, we don't need admissibility. So admissibility essentially means that T satisfies Conet. You have to prove this by hand. I mean, there are no reasons to think that it is true in general. I believe under the saturatedness implies admissibility, but over fields. I mean, if you work over a more general basis, I think there are counterexamples. So you have to prove some kind of Conet. In our situation, the Conet formula you need to prove uses the unipotency of the monodromy, because we need to commute taking invariance by the monodromy and the tensor product. And you can do this under the unipotent condition if you do the tensor product over the cohomology. When you have a semi-simple part of the monodromy, you need to do this based extension I was mentioning earlier. So admissibility is, it doesn't, it's a condition that you have to check by hand, and it doesn't mean that we reduce it to the, it's a new proof of the trace formula in the commutative.
Okay, perhaps let's thank Bertrand again. Thank you.